All right, here we begin our videos for chapter 7. And in this chapter, we're talking all about light and energy and quantum numbers and all those kinds of cool things that get us into how do we understand what we know about atoms and how they go together and how they react with each other and the shapes of them and all that good stuff comes from these foundations. So in order to get to that point, we have to back up and start with light, because this is how physics began to develop the understanding that gave us what we know about atoms and electrons. So light is simply electromagnetic radiation. And the important thing about light is that it travels at a constant speed, which is the important part. Constant speed through a given medium. Okay, and for the purposes of what we're doing in this chapter, we're talking about that speed in a vacuum. Okay, and the symbol for the speed of light is c, lowercase c, 3 times 10 to the 8 meters per second. Okay, now light behaves like a traveling wave. Okay, it also behaves like a particle, but we'll get into that in a little bit. So for any standing wave, let's try again, for any standing wave or traveling wave, why am I saying standing? For any traveling wave, the linear forward speed equals the wavelength times the frequency. Okay, that symbol is lambda, which is the wavelength. This symbol is the Greek symbol nu, which is the frequency. Okay, and our unit of wavelength is meters, and our frequency is inverse seconds, or we can say seconds to the minus 1, which is a hertz, or hertz, Hz. Okay, so whenever you maybe hear about a radio frequency or a television frequency, and it's often given in hertz or gigahertz or kilohertz, it's talking about the frequency of that broadcast wavelength. Okay, so if our light is traveling at a constant speed, and that is the linear forward speed, then c, the speed of light, is lambda times nu. Okay, now an important thing to think about here is that if c is constant, then these are inversely proportional. Okay, so if lambda goes up, nu has to go down. If nu goes up, lambda has to go down, because they have to equal that constant value of the speed of light. Right, so looking at the electromagnetic spectrum, right, so on the far left here, we have gamma rays. That's where you get the Incredible Hulk. On the far right here, we have radio and television. Okay, in the infrared, that's where we get heat. Okay, that's how we cook our food, is sometimes with infrared radiation. Ultraviolet, that's where we get sunburns from. Okay, and in the middle, in this tiny little sliver right here, is the light that we can perceive with our eyes. Okay, that's the visible light. Now, before we get any further, I'd like to point out on the top of this image where it shows this wavy line. Okay, that is the wavelength for these given things, and it's sort of a graphical representation of the wavelength. So if I take a box, let's call that box 1 second. Okay, and I put that right here. Okay, if that light is moving forward at a constant speed, then I get all these peaks in 1 second. Okay, so that's the idea of frequency, right? How many peaks will hit the wall of that box in a given time. Okay, whereas down here, if I make a similar size box, okay, also 1 second in width, right? I get maybe 1 peak that will hit, okay, because everything's moving forward at the same rate, at the same velocity, okay? So longer wavelength gives us a lower frequency. And over here on the left, shorter wavelength gives us a higher frequency. Okay, so inversely proportional. Right now, I don't expect you to have any of these wavelengths memorized. Okay, I don't expect you to know necessarily that green light is somewhere around 550 nanometers, or that yellow light is somewhere just below 600 nanometers. I don't expect you to have that memorized. I do want you to know the boundaries, right, the high and low ends of the visible spectrum, okay, and the colors associated with them, right? And in art class when we're kids, we learned the Roy G. Biv to remember the colors of the rainbow. Well, that's what we're talking about here, okay? Except for in this graphic, the Roy part is on the right. So this would be Roy G. Biv. Okay, so I want you to know that short wavelength is your violet light, long wavelength is your red light. Okay, so long wavelength, low frequency, short wavelength, high frequency. All right, so the next topic to get into is the wave-particle duality of light. Okay, and it was well understood that light behaved like waves. They had all kinds of experimental evidence to support this. But they were starting to see that light actually did other things too that made it seem more like a particle than a wave. Okay, so we have a scientist named Max Planck. He was a physicist, and he postulated that the energy of a system is limited to discrete values. Okay, and that the difference between those values is referred to as a quanta of energy. Okay, so this idea helps to explain one of the things that was troubling classical physics at the time. We're talking about early 1900s, late 1800s, was a thing called blackbody radiation, where classical physics predicted one thing, but experimental results kept showing something else. Okay, so this is the beginning of quantum theory. okay, which was different than classical physics. Quantum physics treats things in terms of discrete energy values. Okay, and Max Planck gave us a very important equation. Energy equals h times frequency. Okay, so E is the energy of one photon. And a photon is a packet of light, okay, basically a particle of light. And it's very important that we remember that this is the energy of one photon, because you will see problems both in the homework and on tests and things like that where you'll be asked for what's the energy of, say, a mole of photons. Okay, so the energy you get from this equation is for one photon. H is Planck's constant. Okay, and it has a value of 6.63 times 10 to the minus 34 joules times seconds. And nu here is still frequency in inverse seconds. We can also write that seconds to the minus 1 or hertz. Okay, so we have this wonderful equation, and where it comes in handy is to explain a thing called the photoelectric effect. Okay, which is, in fact, where Einstein got his Nobel Prize. Okay, contrary to popular opinion, Einstein never won a Nobel Prize for his work in relativity. His one Nobel Prize was for his work on the photoelectric effect. Okay, so what the photoelectric effect is, essentially, is if you have a block of metal, let's change colors here. So if I have a block of metal and I hit it with a wavelength of light, let's say a photon of light, if that light has enough energy, then it ejects, the metal ejects a photoelectron. Okay, and so they knew that this was happening, but they were having a hard time explaining it. And that's where Einstein's work, and hence his Nobel Prize, came in, was that if light was simply a wave, why is it causing pieces of the metal, essentially, to be ejected? That should only happen if light were behaving like a particle. Okay, so big problem, right, for classical physics, because classical physics said no, light is a wave, but the experimental evidence was saying no, light is a particle. So how do we explain this? And this raged through physics for decades, until they actually came up with a decent explanation later on. So metals have a characteristic threshold. Okay, and that threshold is called a work function. Right, so if I hit that metal with a light wave that has greater energy than that work function, an electron will be kicked off. Okay, you exceed the work function, eject an electron. Okay, so the kinetic energy of that electron equals the energy of the light minus the energy of the work function. Okay, so they started to be able to understand how to determine the energy of light waves with these experiments. because they could determine the kinetic energy of the photoelectron. They could determine the work function of the metal. So the difference in those energies has to be the energy of the light wave. Okay, so we're going to go ahead and stop this video here, and we'll pick it up right here on the next video.